welcome back to The Body, the Research, the Professor. Well, you must admit that was pretty fascinating, and we have got more interesting stuff coming up. In the second half of the program, we have got Nick Kirkland with us. Now, Nick's done, I'm going to get you to help me out here, Robin. He's done his Masters
in mechanical engineering.
Yeah, and now he's doing his PhD in biomedical engineering.
Yeah.
Welcome to the program, Nick.
Oh, thanks very much for having me.
Gosh, that's half the program just saying what you've done. It's pretty impressive.
And he's a mix of American, Scottish, English and New Zealand.
A whole bunch, yeah.
Yeah.
It's good to have you here in New Zealand, though.
No, it's great being here. I love it.
And I can't wait for you to start talking about that is behind you. But in the meantime...
I just want to show you this. That's a tiny piece of bone, and you'll see it's got a whole lot of little ridges like a honeycomb in it and lines. And Nick is making the identical sort of thing to replace bone that's fallen out or that's become diseased or become malignant, scrape it out and put in his bone. What's the bone that you're making, Nick?
Yeah, well, basically there's two things we're doing, really. One is we got this new material that we're developing that we think will replace orthopedic materials in the future, and it's got a lot of benefits over current orthopedic materials. And the other thing we have is a process of making this into any shape we want with any sort of roughness. So as you sort of see here, these are sort of channels that we have on this material that we've made, and we can tailor these channels to be any size, so we can actually get the bone to grow in certain directions that we want.
Just let me come to grips with this. What sort of material are we talking about here? What is it? Deeply secret.
It looks just like bone.
Yeah, basically it's a bit of a secret what the material is. Actually, we're developing it at Mechanical Engineering at University of Canterbury, but. Basically, yeah, this is an electron microscope image of that surface, sort of really zoomed up really close. And we can control not only the channel size you see here and the pore size. So this would be a pore here of about 1 millimeter, would be about that big. And we can also actually control how rough it is on the surface, because it's been found that that sort of osteoblasts and bone cells really like a rough surface. So we can control it each step of the process, so we can make what we think will be the ideal orthopedic implant.
Isn't that amazing?
Oh, it's incredible. And it's happening right here in Christchurch.
In the old days, they used to get coral, and they found if you put coral into a person, it would grow bone. So it's sort of all been going, and now don't be too secret. It's metal type stuff, isn't it?
It is
it's
a metal.
That's
alloy.
Right.
It is.
So that's all sort of metals together.
You're right. It is metals,
yeah,
but it's all metals that are.
So you'll be a bionic man, really will.
You're a genuine one. Now, because I'm doing it from a lay person's point of view, and you know, Robin's medical. What size are we talking about? Whatever bit of bone we need
we could make it any size. Basically, with our process, we can take a scan of something, make a 3D model, and then we can make our material in that exact shape.
That's not unlike it, isn't it? Is it?
No.
It's just amazing.
So you'll chop out a bit of bone and replace it with this?
Or a bone that's actually missing already, and we can actually just replace that directly with what we have here. And the real benefit of this material is it'll degrade in the body safely. So it's one operation. You cut the person open, stick it in, one operation, and eventually your body will naturally get rid of the excess, and it's all you after 6 months or a year.
Goodness.
So you you can go through all sorts of magnets and things.
At the airport.
At the airport. But, Nick, I'm a pathologist, so I see people who die, and unfortunately that person had breast cancer, and they get a cancer sometimes in their bone. About 1 in 5 might, if it comes back. And they're gradually learning how to kill that cancer with deep radiation, but the bone collapses. Can you see the day that you could replace that bone?
Yep, definitely.
Because it's so important to get a good backbone instead of getting smaller and smaller. My Aunt Jessie, Auntie Margaret, she got smaller and smaller. She got the osteoporosis and they collapsed.
Right.
Could you put that back in?
Definitely. That's actually one of the best applications for this, because it's a lot stronger than a lot of the other materials out there.
You'll be able to make Aunt Jessie grow again.
And how about those people that the dentists take out the wisdom teeth and they find a great cyst there, and the mandible falls apart? Could you do that?
Yep. Basically anything that was bone, we can replace it with our new material.
Isn't that bloody amazing? No, I mean, you shouldn't say that.
Oh, aren't you naughty? Is this happening now?
This is happening right now, yeah. We're developing at University of Canterbury.
But it's not actually going into people's bodies yet?
Not yet. It takes a little while. We have to make sure it's completely non-toxic, and we have to make sure it degrades at the correct rate, because obviously if it degrades too quickly, you can have problems.
How do you do that? How do you test it on what?
Well, we have a whole bunch of tests, some of them more engineering, sort of electrochemical tests that we have special equipment to do. And other tests, we also do it in animal tests as well, down at the University of Otago in Dunedin. So this is a really big project with the mechanical engineering and the medical departments down there.
What sort of animals do you do the testing on? Does it have to be a big animal or a little animal? Or?
It depends what kind of test you're doing. Just for toxicity, normally you use rats. But then later on, we're hoping to do sheep because they have similarities to humans, and those would be the really interesting ones, I think.
You knew I was once Australian. We used sheep a lot for human experimentation.
No, you know, I think what really surprises me is that all this research is happening right here in Canterbury. That's what I find absolutely fascinating. What made you get into this sort of thing, Nick? How did you get interested in this?
I just think it's a great field. I think it's really interesting. You know, it's a good field to work in. You know, it's good for other people, and it's really, you know, we're really at the forefront, especially with this material. We're really the #1 group, sort of in the world, I think. And yeah, it's great. That's
what the CMRF wants to do, bring engineers together with physicists and hospital people, nurses and all those things, bring it all together. Warmth.
I know, I think that's wonderful. What other sort of scenarios do you envisage using this technology in? I mean, what else? You know, I mean, I know we're talking about bone degeneration and things like that, and you just slot in a new little bit. Are there accidents that can happen that might require this, you know, like any trauma or anything? Car accidents or smashed skulls? I mean, I don't want to get too explicit, but...
It's all primarily to do with bones, but sort of anything where you have bones, even plates, for example, holding things together, or fixtures, this would be perfect for that because unlike current materials where you stick it in there, it's there for life, or it's there until someone else cuts it open and takes it out. This is only there for as long as you need it, and once it's healed, it's gone.
It brings tears to my eyes, but to places like Afghanistan, can you imagine the local people and the soldiers coming back with bits of bone missing that need to be replaced?
And it's just part of the society that we've progressed to, isn't it? That we have stuff that can just disintegrate and go away. It's almost disposable, and we move on and we're fine.
Yeah.
Fascinating.
You're
Great,
wonderful,
Nick. Yes, I know.
Thank goodness you came.
Exactly. Thank goodness you came, and thank you for joining us here today.
Thanks for having me.
Now, after the break, I don't know what Robin and I'll end up talking about, but stay around.